We have a lot of people. So we can start. We can start. After this. We can start. Okay, I think we can start now. Today we are very happy and very excited to have Hitoshi Murayama from Berkeley, also a John professor at IPMU, and he will talk about the two tails of baryogenesis.
Hey, thank you very much for having me here. It's great to be in Davis because I know so many people as old friends. And Marcus and I go back a long way when we postdoc together in Berkeley. Shinchia was a student back then. And since then, we also had a postdoc, John, Cohen, and Veronica. So there has been so many connections between the two places. And so it's great to be here. But last time I was here was probably more than 10 years ago. And that's because 12 years ago, I started a IPMU in Japan, and I was a director, so I had to go back and forth all the time, pretty much like 3 trips a month, something like this. It's been really, really crazy, so I didn't have an opportunity to come here. So when I actually started this job as a director of the Institute for the Physics and Mathematics of the Universe, that's what IPMU stands for, a lot of my friends in Berkeley said, okay, this is way too long a title. We can't remember that. So let's take the beginning and end and shorten it to that one. And I really didn't like this title because it sounded like a lot of responsibility. And it didn't come with enough authority anyway because there's somebody at home who claims she's the voice of God. But anyway, so I've been doing this since 2007. And when IPMU became 11 years old, I got officially replaced by my successor, Hiroshi Oguri. And we look very different style, you can see. And I was very happy to pass the torch. And we did a little transition ceremony. And I wonder if the sound will come out actually, so let me just check. Okay, so hopefully sound does come out. So here's what I did. So I became a free man, so I'm very happy to be here today. And so that also reminds me of a talk I've given actually back in 2003. I was concluding speaker at a leptogenesis conference, and back then I claimed that all of these interesting subjects in particle physics would come together at a TV scale. And I was very optimistic about TV scale physics back then. Now, here we are struggling to do what about the TV scale or beyond understandable physics. And we all know that there had been no signs of physics that would make the Higgs boson natural. So in some sense, many people are struggling in the community about what to do next. And of course, what we know is that the particle physics definitely not all in any sense is a very thriving field because we already know that there are at least 5 empirical evidences of physics beyond the standard model since 1998. And first one is non-baryonic dark matter. Second one is the mass of the neutrinos and dark energy. And the correlation of the C and B is apparently acausal because the photons coming from that direction and photons coming from that direction seem to be correlated. That's the power spectrum, which sounds totally crazy. And that's why we often attribute this to the idea of inflation, that that part of the universe and that part of the universe were together at some point, and that's why they got correlated. And they got separated by inflation, that's why they still are correlated. So once you subscribe to the idea of inflation, then baryon asymmetry really does become an important problem. Because no matter what the initial condition might have been on a baryon asymmetry, it gets totally wiped out by inflation. So we somehow need to recreate, if there were one at the beginning, a baryon asymmetry after the inflation. So now this becomes a well-defined question to ask. So at least we don't understand these 5 things. And they are not based on any of the theoretical arguments, naturalness, and so on and so forth. They are there, they are glaring at us, and they are in our face, and we have to actually think about this. So definitely there are a lot of interesting problems to work on. Of course, one problem though is that we don't really know what the energy scales are, but nonetheless, today, I'd like to focus on this question of baryon asymmetry. That's why the title is Two Tales of Baryogenesis. And the first half has to do more with the neutrino mass, because it relies on the idea of leptogenesis. Second one relies on the electroweak baryogenesis. So I will talk about these two possibilities and ask about experimental consequences. But first thing first, what do we know about the baryon asymmetry? So one very good measurement people have done on the deuterium abundance relative to the hydrogen is by looking at this the absorption lines by a hydrogen gas which intervenes the line of sight from, let's say, quasar at large distances and our observations on our planet. And so the idea here is that you look at the absorption lines, and most of them are nearly saturated. So here you don't see any photons at all. But the point is that if you look at the absorption line of a hydrogen-like atom, and then energy levels are given by mu, which is the reduced mass of the system. So depending on whether you're looking at the hydrogen, which is the bound state of proton and electron, or deuterium, which is the bound state of deuteron and the electron, then the reduced mass between the two systems differs by something like 1 part in 4,000. So it's a small difference, but nonetheless, all these absorption lines are shifted for the deuterium relative to that of the hydrogen. And this little dip, which appears on the shoulder of the hydrogen absorption line, give you an estimate of how much deuterium there is in this intervening gas. So that's how people have measured the ratio of the deuterium to hydrogen, even though chemically they are totally equivalent to each other. And so they also measurement now from the CME power spectrum. So this is from the Planck data on what the amount of baryon there has to be at the time of recombination. And by putting these two information together, we can infer the amount of baryon to photon ratio from the BBN, that's this wider band, and from CNB, that's the narrower band, exactly on top of each other. And this is really amazing because the measurement from the Big Bang nucleosynthesis that created this primordial deuterium has to do with the physics that happened only 3 minutes after the Big Bang, while the measurement from CMB has to do with 380,000 years after the Big Bang, and they give you the same number. So that's how we believe that this is the correct number to think about, namely that the baryon to photon ratio is less than 1 part in a billion. So that's the problem. So we need to have both the baryon to photon ratio as small as 10 to minus 9, but certainly not 0. And what that means is that after the inflation, when reheating happens, or the energy density of the inflaton went into the thermal bath of the universe, then of course creating matter from the energy always has to do with the 1-to-1 ratio between matter and antimatter. So you have this kind of situation right after the inflation. But what we need is some physical process that takes 1 out of a billion antimatter and turn that into matter somehow. We don't know how, but this is necessary so that we could have survived. So pretty much all of them have annihilated. So you are here at the expense of billion friends. So you have to be very grateful to them. But nonetheless, we really need this mechanism of changing 1 part of a billion antimatter into matter so that we could have survived the Big Bang. So, somebody saved us from complete annihilation. So the question is who that is and when did it happen? And of course, this is just a single number. So there have been so many theories for this to explain this single number. And of course, we don't know which one is the right one. So really the question here is that once you think of some mechanism for the baryogenesis, are there any testable predictions so that we will know at some point which one of these pile of papers turns out the right theory for explaining why we could survive this near total annihilation? So that's the question. So hence, I'm going to talk about two tales here. So one of them is the idea for leptogenesis, which is an idea originally by Fukugita and Enagita back in the 80s. And the idea here is that this has to do with the origin of neutrino mass. And the problem with this idea is that it happens at a very high energy scale, so at very high temperatures. I'll tell you what the numbers are in a few minutes. And so if you have something happening at very high temperatures or high energies, it will be very difficult to test that experimentally. And so in some ways, people sort of even gave up on the idea that it's not testable. So at least we came up with one idea, which may go back to the era when universe was going through this process of creating baryon very, very early on. And that can actually lead to a signal of gravitational waves. And that's an idea I worked out with these people. And happily was successful PRL with Edison's suggestion. So that's the first half of the talk I'm going to present today. And second half is the other idea, popular idea, called electroweak baryogenesis. But I will tell you again in the second half that electroweak baryogenesis was so attractive because it's happening at the electroweak scale. It may be testable directly by collider experiments, and that was the source of the excitement that it's a testable theory of electroweak baryogenesis. It turns out that it's too testable. It is practically excluded by now. So you can't talk about electroweak baryogenesis in a plain vanilla way anymore. You have to do something about it. So the question is, if you do something about it, does that still retain sort of testability idea of the baryogenesis model at the TeV scale? So that's the second half of my talk today. So let me get started with the leptogenesis, which is happening at a very high scale that has to do with the neutrino mass. So how do we test this? In conjunction with another thing about neutrino mass called Seesaw mechanism. I'm going to explain this in a few minutes, by using gravitational waves. So that's the first half. So I believe everybody here knows that we have discovered the mass of the neutrinos, originally relying on atmospheric neutrinos, which had been generated by the cosmic ray protons striking the nuclei of the hydrogen and nitrogen in the atmosphere, and that's sort of the fixed target experiment happening up there at about the 20-kilometer altitude that produces a bunch of pions. Pions decay into muon and muon neutrino, and these muon neutrinos sneak into the detector like super Kamiokande and causes a reaction. And this was actually supposed to be a nuisance because these experiments had been built for looking for proton decay. And if you're looking for proton decay, the proton inside this water tank all of a sudden pops. And that's what they were looking for. But if the neutrinos come in like this and cause the reaction, that also looks like something pops in the detector. So this was a main background. And when you're looking for proton decay, that's why people studied very hard. And to study this very hard, one thing people realized is that this kind of neutrino events caused by the neutrinos producing the atmosphere has to be up-down symmetric because of the symmetry, simple geometrical arguments. So we know the cosmic rays come from random directions because they had been randomized by the magnetic field inside a galaxy, presumably coming from some past supernova explosions. Here they are. And so because it's random, suppose you have this reaction happening in the atmosphere up there, producing neutrinos that come into your detector with this angle theta, which is called the zenith angle because that's the angle away from the zenith. But because we know that our planet is a pretty good sphere, and if you extrapolate this line all the way to the other side, then this is an equilateral triangle. So this angle here is the same as that angle, which is also the same as that angle. So what could have happened here, exactly the same thing can happen over there. So you expect the neutrinos coming from above, with zenith angle theta, to have the same rate as the neutrinos coming from zenith angle pi minus theta. And so that was the expectation. And I happened to be at this neutrino conference back in 1998, where the Kajita gave a presentation on the results from Super K, where he changed the title of the talk on the spot, changing from the recent result on atmospheric neutrinos to the evidence for neutron oscillation in atmospheric neutrinos. And that was really exciting. And this was his the main slide. So if you look at the electron neutrino events, these hatched boxes are the Monte Carlo projections. This is the cosine of zenith angle. So here is the downward going neutrinos, theta equals 0, and this is the upward going neutrinos. And theory projection is indeed up-down symmetric, and so are the data within statistical error. But for the muon neutrinos, again the theoretical projection is up-down symmetric, but the data clearly are not. And he just took this ratio on a counting experiment between upgoing neutrinos versus downgoing neutrinos, and this was away from 1 by more than 5 sigma, hence that was a discovery. So, so we learned that neutrinos actually disappear So half of the neutrinos which had been generating on the other side of the Earth now disappeared because had not been detected. And at this point, it was not clear what should be the interpretation of the data, but of course we learned over time that this is an evidence that neutrinos oscillate. And so the half of the muon neutrinos generated on the other side of the Earth had oscillated mainly to tau neutrinos, which did not get detected by the super Kamiokande detector. So this remaining half are supposed to be tau neutrinos. And much later on, they found some weak evidence that indeed tau neutrinos are there in the atmospheric neutrinos after oscillation. So this, in the end, told us that neutrinos have mass, because if neutrinos oscillate, so those coming from above didn't have enough time to oscillate, but those from the other side of the Earth had enough time to oscillate. That's why half of them got lost. But what that means, the neutrinos sense time, and if the neutrinos doesn't have a mass, it's going with speed of light, then clock stops, and they should not sense time, but they do. That's what this data says, and hence the neutrinos are not going with the speed of light, therefore they have a mass. So that's how people discover the mass of the neutrinos. I played a small part in this business. I joined the Kaplan experiment later on, which had, instead of water tank, has the liquid scintillator, basically oil in it. And we detected the neutrinos coming from the power plants, nuclear power plants. And those days, before Fukushima, there were plenty of power plants in Japan operating. And most of them were at the distance from Kamioka by about 175 kilometers. So we could take data and measure both the energy and the of the neutrino events and the rates. And that's how we came up with this plot. So what you can see is that from the amount of neutrinos expected from the reactor experiments done less than 1 kilometer away from the reactor sources, they do disappear and come back, and disappear again and come back. So we at least see 2 oscillation cycles, and that was very exciting for me. And the leader of the experiment was Kunio Inoue, and I play small parts of my pictures, that's why small compared to Kunio. But anyway, so we learned that neutrinos do oscillate and therefore have finite mass. But as we all know, it's very light compared to any other elementary particle masses we know, hence that's the puzzle. And the sort of most popular idea to understand why neutrinos are so light is because of what is called the Seesaw mechanism. So Seesaw mechanism is supposed to explain why neutrino mass is so light by introducing a new particle degree of freedom beyond the standard model, namely right-handed neutrinos. It's called N in this on this slide. And the right-handed neutrino doesn't have any standard model quantum numbers, so they can have the mass on its own without relying on the Higgs mechanism. So this mass can in principle be very large, even up to Planck scale in principle. On the other hand, in all generality, right-handed neutrino can have the usual Yukawa coupling to left-handed neutrino, picking up the mass from the Higgs mechanism. So what this gives you is the mass matrix between the right-handed and left-handed neutrinos, where this YV piece is supposed to be sort of similar to all the quark and lepton masses we know and love. But this additional piece M, which is unique to neutrinos, because none of the other right-handed particles are neutral under the standard model quantum numbers. So this is specific to the neutrino case. And given that this M can be arbitrarily large, if you diagonalize this matrix, you find that you find that a very light neutrino. So the cartoon here is that if you take this YV piece coming from the Higgs mechanism, it's similar to the quark and lepton masses, so that's too big for the mass of the neutrino. But once you bring in something really big for the right-handed neutrino, then Seesaw goes down like this, so this one becomes even lighter. So that's the idea of, I suppose, Seesaw mechanism. So in the end, the mass of the neutrino we observed is suppressed by the ratio of the Higgs scale, 250 GeV squared, over some very big scale M, which turns out to be something like a 10 to the 10th GeV or beyond. It's a very big number. So that's the idea of the Seesaw mechanism explaining smallness of the neutrino mass. But this actually comes with an added benefit, because an early universe, even though this white-hand neutrino is very heavy, right after the Big Bang, presumably they had been produced. And they eventually decay. When they decay, they use this Yukawa coupling. And so I changed the notation to H from Y, but it's the same thing. And it turns out that when you actually look at this tree-level diagram, because the white-hand neutrino is actually Majorana fermion, decays with equal probabilities into lepton final state and anti-lepton final state, 50-50. But once you pick up this decay now interfering with the one-loop diagram, and there's an imaginary part of this one-loop diagram, and that interference can make a difference between the branching ratio of this white-hand neutrino decay into lepton final state and anti-lepton final state. And this is actually exactly the same mechanism we have already seen in kaon physics called epsilon prime of epsilon, direct CP violation, and many more examples in B physics now. So we know nature does this. And once this happens, then this is the origin of the baryon asymmetry, namely that you start with a large number of these white-hand neutrinos. They just hanging there after for a while until the age of the universe reaches their lifetime. Then they start to decay, but when they decay, the branching fraction into matter and antimatter are different from each other. So then there's an asymmetry between the leptons and anti-leptons after this decay happens. So this is, I would say, the Darwinian paradigm in neutrino physics these days. And this is a very interesting thing because, smallness of the mass of the neutrino is actually probed to this very high energy scale. So that's a great thing. But at the same time, because we're talking about this very high energy, high temperature phenomenon, these ideas are notoriously difficult to test. But just to reinforce the point that this idea does lead to baryogenesis because it does satisfy all three criteria put out by Sakharov, namely that you do need baryon number violation. And we have baryon number violation because standard model anomaly process actually converts baryon to lepton numbers to each other. On the other hand, Majorana mass of the neutrino violates the lepton number. So as a consequence, baryon number is violated as well. So the baryon number is violated with the Seesaw mechanism with the Majorana neutrinos. The CP violation is in this Yukawa matrix of the left-handed and right-handed neutrinos in a very much similar way to the Kobayashi-Maskawa phase for the quarks. It turns out that thanks to the fact that there's additional complex number, which is the Majorana neutrino mass for the right-handed neutrino, even 2 generations would be sufficient to have CP violation, unlike for quarks, which requires a minimum of 3 generations. So in some sense, CP violation is even easier in the neutrino sector. Finally, you can also have a departure from equilibrium because these right-handed neutrinos may have very weak coupling, or Yukawa coupling. So once they are produced, they don't decay right away. So that's why they go out of equilibrium, stay in the thermal bath until their lifetime is reached, and only then they start to really decay. So out of equilibrium is also very easy to achieve. So people have looked into great detail quantitatively whether this mechanism works at all. And so this is one such a study by Dipole, Plumov, and Buchmüller already some time ago. And here's what they call successful region. The horizontal axis is some combination of neutrino masses, which doesn't correspond to the neutrino mass eigenvalue of the observed 3 neutrinos, but it's supposed to be of the similar order of magnitude. And given the scale put out by this atmospheric neutrino oscillation, which is like a 5 times 10 to the minus 2 electron volt, which is here. So these are sort of the natural order of magnitude you can talk about for this combination of masses. And vertical axis is the mass of the right-handed neutrino, presumably the lightest one among them. And successful region, which does achieve the correct amount of baryon symmetry, is somewhere between 10 to the 9 GeV and 10 to the 15 GeV or so. So we are talking about very high energy scales. So this works without much of a fine-tuning or anything, so very natural. I even did a Monte Carlo on how often you can get the right baryon asymmetry of the universe using this mechanism with Xiaoshan Lu, who used to be actually postdoc here. And there was a wonderful peak around 10 to the minus 10th, and that's the number you want. So in some sense, without doing any fiddling with the parameters, getting 10 to the minus 10 from baryon asymmetry is very natural in this mechanism. So it works great.
So that sounds like a statement that depends on some measure on the right-handed neutrino mass.
Right. So what we did is to take the linear measure on the right-hand neutrino mass, and on the mixing angles, it turns out that there is something called a Haro measure for the group theory, which is both left and right invariant. So there's a good reason to actually take that measure, and then varied everything by Gaussian around it. And so at the end of the day, so that measure, the distribution turns out to be really beautifully peaked around 10 to the minus 10. So, but the real question is, how do we test it? So suppose you would like to create these right-hand neutrinos by building a collider that reaches 10 to 14 GeV. With the current technology, we need the collider to be as big as that. And so that clearly requires not only international, inter-agency collaboration, but presumably interplanetary collaboration too. So I don't think I'm going to see this one during my lifetime. So we have to come up with something else. And so what people do talk about in the idea of trying to test this idea of seesaw mechanism leptogenesis is along the direction what I call archaeology. Namely that you look for some circumstantial evidences by digging up fossils. So they are not really proofs in a direct way, but if you are in the archaeology business, you can recreate the history. You look at the relics from the history, and you try to reconstruct the story based on the relics you observe. So we try to do something similar. And so the kind of relics we do talk about in this context is the neutrinos of mobility decay, because that will test the idea whether neutrinos are Majorana or maybe Dirac. And we would like to see that there is indeed CP violation in the neutrino sector. For example, Dune in the United States, looking for CP violation in neutrino oscillation. And the reason why this is not really proof of the leptogenesis is because the CP violating phase in neutrino oscillation is what is called Dirac phase, while what's relevant for leptogenesis is what is called the Majorana phase. So they could be totally independent from each other. So that's why it's not a proof. But nonetheless, it's a circumstantial evidence.
Did the Monte Carlo you referred to before that predicted 10 to the right range include
Yes.
CP violations?
Yes.
Between
Yes. And it turns out that, again, by looking at the Monte Carlo, then the Dirac phase and Majorana phase are totally uncorrelated. So of course, if you specify a model, you may find a model where they are correlated, but that's a very model-dependent statement. So on general grounds, they're just totally different phases, unfortunately.
Excuse me, I assume there are no other examples in particle physics that help lead the way about that point, about the two different CP violated phases.
Yeah, I'm not aware of one, yeah. And we may be also a little bit lucky, so we may start seeing some processes of the lepton flare violation like mu2e experimental formula right now. And so in this case, this sector of the right-handed neutrino at high energies would affect some low energy observables. Let's say if there is a supersymmetry, maybe beyond TeV, but there may be some renormalization effect on the mixing among the scalar leptons because of the presence of right-handed neutrinos, and they can induce lepton flare violating processes which are at observable rate. So that may be another circumstantial evidence. So we collect these relics and then try to tell the story out of them, and that's why I call this archaeology. So this is sort of like, some people might not like this, but this is sort of like bringing the seesaw mechanism and leptogenesis to a civil court. We don't have direct evidence to prove them are guilty in a criminal court, but maybe we can convict them in a civil court, so that's the idea here. So for that purpose, we better have as many circumstantial evidences as possible. So this is the list people used to talk about. Could there be anything else? And that's the question I ask myself. And my answer already, gravitational waves. So how does that work? So we have this very high energy scale to right-hand neutrinos, up to 10 to 15 GeV or so. But it's not quite in Planck either, because nothing forbids the mass of the right-hand neutrino at the face value. It could have been as high as Planck scale, but it's not for the purpose of getting the leptogenesis right. So it's not a without loophole, but it's kind of natural to think that the mass of the right-hand neutrino is also a consequence of some kind of the symmetry breaking. So Planck scale, right-hand neutrino is still massless. But at some low energy scales, asymmetry breaks, and as a result, right-hand neutrino picks up a mass. And that seems like a sort of a plausible way to think about this. So if that's true, there can be a phase transition around these energy scales. The question is, does that kind of phase transition lead to gravitational waves we can observe? It turns out that phase transition itself is unlikely to give us gravitational waves we can observe. And this is for a totally different model, but this is a pretty generic idea on what happens on the gravitational waves when you have a first order phase transition where you create bubbles and bubbles coalesce and so on and so forth, leading up to gravitational wave signal. So the first thing to notice is that if you increase the temperature for the phase transition, the spectrum moves to the right, namely to higher frequencies. And LIGO range is here, Lisa range is there. So already for like 1000 TeV, we are barely in the LIGO range. So if you go up to 10 to the 10th GeV, 10 to 15 GeV, you're way to the right. So that's really not in the window where any conceivable forthcoming experiment can see gravitational waves. So it's just a totally different frequency range. But there is another way that we may get gravitational waves, and that's the cosmic strings. Sorry for a little technical slide here, but suppose you have additional symmetry like U1B minus L. That's a well-known gauge symmetry you can have beyond the standard model. And suppose this gauge symmetry is broken by some wave of the scalar field, so that it generates the mass of the right-hand neutrino, either to the linear power or second power. That distinction turns out to be utterly important later on. But anyway, so if you do break U1, it leads to cosmic strings, because it's the same physics of the type 2 superconductor. So in the superconductor, you break U1 electromagnetism by the condensation of the Cooper pairs, which are charged electrically. And that breaking of U1 symmetry would lead to the flux of magnetic tubes, tubes of magnetic fluxes punching through a piece of superconductor. And that's why we do this underground lab experiment where a piece of magnet, the superconductor floats on a magnet. So we know this happens when U1 gauge symmetry breaks. And it turns out that if this kind of thing is created in the early universe, which does correspond to very high frequency, as I mentioned earlier, this network of cosmic strings actually is there for a long period of time. And Andy knows much better than I do about this because he was really working on the cosmic string stuff before. And it turns out that this behavior of the network of cosmic strings would lead to very nearly scale invariant spectrum all the way down to much lower frequencies where we have hopes of detecting them. And so that is what is called the stochastic gravitational wave background. So this is a simulation I borrowed from LIGO website. So this is the initial network of cosmic strings at the time of the phase transition. And universe expands. And so this animation shows always the same size where things coming from outside, so that this is the size of the horizon in early universe. And what you see here is that the network evolves, but they look pretty similar all the time. So this is the scale invariant behavior of the network cosmic strings. And what they do is that energy of a string is proportional to its length. So they would like to minimize the length of the string. So they try to simplify its own network by cutting through and recombining and so on and so forth. So in this process, it is expected that gravitational waves are emitted. So what we use is this value called string tension, mu, which is basically the asymmetry breaking scale squared, and g is the Newton constant. So the amount of gravitational waves you produce from this evolution of the cosmic string network is roughly proportional to this combination, which is symmetry breaking scale squared over m Planck squared. And let me skip this slide because it looks like I'm going a little bit too slow. So then one can ask the following question. So suppose you want to have this new symmetry for the phase transition that forbids the mass of the right-hand neutrino, but can generate as a consequence of the phase transition. And we want to make sure that new gauge symmetry must be anomally free with a minimal particle content, standard model, and right-hand neutrino, but nothing else. we don't want to also make the gauge group very big. Standard model gauge group is rank 4, so let's say only one extra rank, or 5 and less. We also need to make sure that this symmetry breaking does not lead to any magnetic monopoles, and that's the slide I skipped. If you have the magnetic monopoles from phase transition above 1,000 TeV or so, that would would overclose the universe, would be overabundant, so you can't have that. So if you make these requirements, it turns out that there are only a finite number of possibilities. You can completely classify them, and you can embed the standard model fermions into this gauge groups and so on and so forth. And the main point of this table is that more than half of the possibilities, like these and an additional one over here, actually does lead to this network of cosmic strings, just because of the topology of the symmetry breaking. And one thing to note is that even when the high energy gauge group doesn't contain U1 dot breaks, you can still have a string if the low energy gauge group has a discrete symmetry in it. And that's kind of quite natural to have, because if you want to generate the mass of the right-handed neutrino from the Yukawa coupling to this new Higgs field, then it turns out that this symmetry breaking would preserve what we call the matter parity, namely flipping the signs of all the matter fermion fields, and that was originally part of the gauge group. So even when you don't break U1, so this is trivial, but when the low energy group has this discrete Z2 in it, it turns out that the coset space has a non-trivial topology, so you do generate cosmic string network. So if you put everything together, so we have this symmetry breaking at very high energy scale, and more than half of the possibilities would lead to the formation of cosmic strings. And that cosmic strings would try to simplify itself over time, and that would generate this scale invariant spectrum of the gravitational waves. And that comes into this frequency range relevant for all of these experiments. And for the range of symmetry breaking scale we talked about, from 10 to the 9 to 10 to 15 GeV, and if you wait long enough for the future missions, like the Big Bang Observer or DeCigo, then they actually did cover basically all of the range of the parameters for the Seesaw mechanism. So that's the main message. So leptogenesis is notoriously difficult to test, but if you do find gravitational wave signal, which is nearly scale invariant, then that's a telltale sign that this has to be due to cosmic strings. And the height of this spectrum tells you what the energy scale is. So you can see that energy scale turns out to be in the right range for the Seesaw mechanism and leptogenesis. And by verifying that it's cut off at the right point, which has to do with the size of the strings generated originally, then you can really confirm that it is indeed due to cosmic strings. So, so that will be a very exciting signal to observe. One thing we also noticed in addition is that all of the gauge groups I mentioned earlier happens to be embeddable into the grand unified theories based on SO10 group. So it's quite natural to think that everything is embedded in SO10. And this actually led to some interesting paradox I had to think about it for a while. Suppose SO10 breaks the standard model directly, then you don't predict any strings. But if SO10 breaks to U1B minus L first, and then U1B minus L is broken later, you do predict cosmic strings. So what's going on? So it turns out that in this situation, then the strings are unstable. Remember, the strings is basically like a tube of magnetic flux, like in superconductor. But for this breaking, the grand unified theory predicts the existence of magnetic monopoles. And for this breaking, it turns out that amount of magnetic flux inside a tube can be saturated and end on the magnetic charge of the magnetic monopole, namely that you can create monopole-anti-monopole pair to cut a string, like this. So you have this cosmic string, but you create a pair of magnetic monopole and anti-monopole, and that's actually a tunneling phenomenon, which is known as Schwinger effect, which is basically the same thing as having a very strong electric field, but then the electric field will create a pair of E plus E minus, and that would reduce part of the electric field you have applied to. And so that's what's called Schwinger effect, and you know how to compute that. So in this symmetry breaking pattern I mentioned, starting from SO10 unified theory to standard model times U1B minus cell, and then U1B minus cell breaking, the size of the magnetic flux is exactly such that it can be saturated by the magnetic monopole. Of course, if the size of the magnetic flux is half that, which happens for actually superconductor itself, because what condenses the Cooper pair has charge 2e, so magnetic flux is h over 2e instead of h over e. So in that case, it cannot. So magnetic monopole can change the orientation of the magnetic field, but it cannot cut it. So it depends on which symmetry breaking you have. For this case, strings are still stable. It can have this pair production, but it doesn't decay. But for this case, it does. And as I said,
what is Q?
I'm sorry?
What is Q?
Q is the charge of the Higgs field. So if you break U1B minus cell with a Higgs field with charge Q, just like for the Cooper pairs in superconductor, magnetic flux inside the cosmic string is h over Q. And this is the charge. So you can have a fractional magnetic fluxes depending on the charge of the Higgs.
Okay.
So if this is 1, that's exactly what corresponds to that can be cut by magnetic monopoles. If it's 2 and beyond, then it's a fractional magnetic flux, so it cannot be cut by the pair creation of magnetic monopoles. So that's the Schwinger effect. And what we know how to compute this effect in 3 plus 1 dimensional QED. What you do is to reinterpret this by taking dual between magnetic and electric. So you're talking about pair creation of magnetically charged particles in the magnetic field in 1 plus 1 dimension. And you can do that. And it's a tunneling phenomenon. You can see this exponential suppression going on. And this exponential suppression factor basically goes like exponential of the monopole mass squared of the magnetic field, which is the same thing as saying this is the SO10 scale squared over the B minus L scale squared. So depending on the ratio between two energy scales, if the ratio is infinitely large, then the strings basically becomes practically stable. If the scales are close, they may break by the pair creation of magnetic monopoles. It turns out that this idea of seesaw mechanism can further be extended into including inflation itself, or the hybrid inflation model. And so in this kind of model, it has to be at a very high energy scale, even beyond 10 to the 15 GeV, to get the correct density fluctuation spectrum for inflation. And because the scale is high, this ratio between two scales is not that large, so this tunneling effect can be sizable, and it turns out the strings can really be cut, depending on the ratio between two scales. So it's a ratio of 6, 7, 8 or so. So we normally think that the grand unified scale is something like 2 times 10 to the 16 GeV. So this one will correspond to a few times 10 to the 15 GeV. And so the gravitational wave spectrum then gets cut off because the strings disappear. And it turns out that for this very high energy scale, the Bochum-Muller company really talked about this inflationary model, and they had to sort of abandon that idea because there is really a constraint from pulsar timing array, which is in this darker shade, which is difficult to see on the slide, I apologize. But prediction is here for the energy scale of their interest, but it's already excluded, so they sort of abandoned that model. But thanks to the fact that energy scale is high in their model, then it can be cut off like this, so you can evade this limit from pulsar timing array. But you still do predict sizable signal at LIGO, or maybe some advanced form of LIGO in the future, or better yet, the Einstein telescope, which is being planned in Europe. So this is the model where you do both inflation and also the seesaw and leptogenesis at the same time, which requires very high scale of symmetry breaking, which turns out to still give you observable gravitational wave signal rather in the near future, but can be still consistent with the existing limits from pulsar timing array. So that's the story here for the first half of my talk. So the conclusion of the first half is that stochastic gravitational waves are another possible circumstantial evidence for seesaw and leptogenesis. For gauge groups with rank 5 and less, more than half of those possibilities produce cosmic strings. And if you include the future missions like BDO and DISIGO, they do cover most of the range of energy scales relevant for Seesaw mechanism and leptogenesis. And if you do detect scale invariant gravitational waves, it helps not only establishing Seesaw, but also the breaking pattern. And if strings appear to have this cutoff at some energy scale, that can be even taken as an evidence for grand unification, because if the strings are cut, that shows that's an evidence for the existence of magnetic monopoles, which really smells like you have a grand unified theory. But at the end of the day, one important question to ask, especially for the experimentalists in the audience, is whether there is any way to detect gravitational waves at higher frequencies than LIGO range we know how to do, because higher temperatures for the phase transitions always correspond to higher frequencies in gravitational waves. So if there's a way of detecting those, that will be even more direct probe of what happened very early on in evolution since the Big Bang. So that's an open question. I'm aware that some people are already talking about this, but no concrete, real, realistic ideas yet. So this is an open question, and hopefully some people in the audience might want to think about it. Okay, that's the end of the first half. Any questions? Yes?
Just remind us one more time, that last bullet point, what's the target frequency?
Yeah, of course that depends on what energy scale it is. So let me show the same slide again. So what this is showing is that if we have symmetry breaking at say 1000 TeV, 10 to the 6 GeV, then you do have gravitational waves in sort of LIGO range. If you go to 10 to 10th GeV, that's the lower end of the Seesaw mechanism, then you go 4 orders of magnitude higher, then you're talking about like a 100 kilohertz or megahertz. So that's the kind of range we are interested in, and once again, we don't know how to do that. Yes, Andy?
So a comment about scaling laws for cosmic strings. So long time ago, I worked on cosmic strings, and we all loved the idea of the scaling law. And then we realized that the arguments we were making for the scaling law weren't very good, and they were based on kind of wishful thinking, and there was really much more dynamic and complicated problem. And my impression was that then the people like me were discouraged by how complicated it was, and then worked on other things. And people who remained convinced themselves that there was some way to argue for scaling stuck with it. And so there's a sort of selection effect. There's a lot of belief in the scaling law, but it could easily be different from that.
Well, so
and that might, I mean, I don't know if I'm really being helpful or not, but I couldn't resist noting that it could be different.
That's a very
it might even be helpful in some ways.
So certainly, I did rely on recent calculations of the gravitational wave spectrum from cosmic screen network. And as you see, the calculations we rely on still does show this near scale invariance over many decades. But there is still controversy about this. The controversy has to do with a different question, namely that when the strings simplify themselves by recombination and resolving cusps and so on, do they lead to gravitational wave emission, or do they lead to particle production? Because there's a symmetry breaking, there are heavy H boson, heavy Higgs boson. If the energy is lost into particle modes, then sort of efficiency going to gravitational wave will be small. And this has been a long-standing controversy. And from what I studied from the literature, there is a recent paper by Vishkari and company last year, which seemed to have settled this issue by trying to compute both particle production and gravitational wave production for relatively smaller-ish string groups. And he and his group discovered that the particle production is suppressed exponentially from long loops, while they can dominate for short loops. And what the string network predicts from the phase transition is that you have a spectrum of length of these loops. So even if the short loops end up going more or less into just particles, the long loops still give you the gravitational waves. At later stages, they are dominated by long loops anyway. So it looks like this the estimate of the gravitational wave, it still stands. And that's the latest controversy I have seen in the literature, and that seems to be on the way of going up. But that's the best I know.
Yeah, I think there's more to say, but I don't want to slow you down.
Okay.
Hear the rest of your talk.
Any other questions? All right, so the second half is actually a lot easier. So that's the idea that we actually create both dark matter and the baryons from asymmetry from a first order phase transition in the dark sector. So just again a little review, the Sakharov conditions are satisfied actually in principle in the standard model, but didn't work out. So the baryon number violation I already mentioned baryon number is violated in the standard model from the electroweak anomaly effect. CP is violated by Kobayashi-Maskawa phase, and non-equilibrium could have been achieved if the phase transition of the electroweak symmetry breaking were first order phase transition, because the first order phase transition means you have the coexistence of two different phases, which is certainly is departure from equilibrium, just like the vapor condensing into liquid droplets. And so this could have been the case. And if this is the origin of baryon symmetry, everything happens at the electroweak scale, so it could be experimentally testable, and that's why there was a lot of excitement behind this idea. Over the years, we learned it doesn't work. Kobayashi-Maskawa phase is just way too small. Not necessarily that the phase is small, but phase always come together with Yukawa couplings in standard model, and Yukawa couplings are small in a standard model. So if you look at something called the R-scope invariant, which is the only combination you can build out of the standard model Yukawa couplings, which is independent of the choice of the bases, then this quantity turns out to be something 10 to minus 20th. So even if the baryogenesis itself is 100% efficient, you can't generate more than 10 to minus 20th. So that was basically the end of the story. And in addition, now that Higgs boson is discovered to have a mass of 125 GeV, the first order phase transition doesn't look possible either, which would have required Higgs mass less than 75 GeV. So the phase diagram of the standard model people worked out in the lattice calculation. This is the mass of the Higgs, this is 75, and if you raise the temperature, for let's say 60 GeV mass of the Higgs, then if you raise the temperature, you do hit this line where you expect first order phase transition, and so it could have worked that way. But 125 GeV is way in this direction. So everything is smooth and continuous. There isn't even a phase transition to speak of. It's actually a crossover. So it's sort of like the phase diagram of water, where liquid phase and gas phase are continuously connected at high pressure. So it's very similar to that, and it's a crossover. There's no phase transition. So standard model per se doesn't work, but it could be something similar to the standard model, which was really pushed forward by Cohen, Kaplan, and Nelson, and I really was saddened to hear the news of the passing of Ann Nelson. She was really one of the giants in the field. But anyway, what they proposed is the following idea. So we first want to change the standard model in a way that somehow we have this first order phase transition. So then you have this coexistence of two phases, one without the Higgs expectation value and the other with the Higgs expectation value. And the bubble with the Higgs expectation value will start to grow because it has lower energy. And while the bubble is growing, then you have particles on this side of the phase that get scattered by this bubble wall. Let's say top quark, because it has the largest Yukawa coupling to the Higgs. And this reflection of the top quark off the bubble wall can go from T left-handed top quark to right-handed top quark, left-handed anti-top quark to right-handed anti-top quark, right-handed top quark to left-handed top quark, and right, and so on and so forth. And if you have a CP violation in this interaction of the top quark with the bubble wall, then those probabilities may be different from each other. So while they're doing just reflection off the wall, you can start having the different number of the left-handed top quark from its antiparticle, right-handed top quark from its antiparticle. Nothing violates the baryon number here, so top left plus top right is still the same as anti-top left plus anti-top right, but individually their numbers may be different from each other. So that's the consequence of the CP violation in the bubble wall. But once this asymmetry is there, you haven't broken baryon number yet, but Spaderon effect can convert left-handed top quark to left-on, but not the right-handed top quark, because Spaderon effect is SU2 gauge interaction, which couples only to left-handed particles. So T left can be now lost into leptons, but T right stays. So because of these asymmetries you generated, then if you actually start losing T left this way, you had less T left than anti-T left initially, so once you actually lose it, you end up having a positive baryon asymmetry now, compared to the amount of anti-top core you have in the system. So this is the way you can actually generate a baryon asymmetry by this scattering of the bubble walls. And more recent studies showed what they initially proposed didn't quite work either. What you really need is that some kind of CP violating phase changing across the wall of the bubble. If it's a static CP violating phase, then you don't get enough. You need to have basically the spatial variation of CP phase within the thickness of the bubble wall, and that's what I learned from Gerald and Sylvan. And so there are a lot of requirements in this. So fixed Kobayashi-Maskawa phase doesn't help. You really need CP violation in the Higgs sector. Yes?
Does this only work for heavy quarks?
Because you need to have the strong coupling to the bubble wall. Yeah. So the light quarks are totally relevant for this purpose. So again, there's some additional requirements. And also, the amount of baryon you generate is already suppressed from the beginning, because it has to go through sphaderon, and people estimated the rate of this sphaderon interaction to be something like 10 to the minus 6 times temperature. And what we want to generate is like 10 to the minus 9. So what we need is that, well, first of all, we need some new physics so that the electroweak phase function does become first order, which is not possible for the minimal standard model. We need to modify the Higgs sector somehow. And also that there's only 3 orders of magnitude you can lose here, so the size of CP violation and the efficiency of generating a symmetry has to be bigger than 10 to the minus 3. That's an additional requirement. Having learned that, we looked at the latest data on the limit of electric dipole moment that appeared in October 2018. So the electric dipole moment of the electron is incredibly tiny, less than 10 to the minus 29 centimeters. And so if you remember the definition of dipole moment, this is the sort of distance between the opposite charges, right? And we know electron has to be smaller than 10 to the minus 17 centimeters. That's the current experimental limit. This is 10 to the minus 29. This is an incredible strong limit. It's amazing that they can do this kind of experiment. And in any theories which have some new CP violation in the Higgs sector, you can draw diagrams like these. It's typically called bar Z diagrams. It's 2 loop. But if we have order 1 CP violation, this could still be sizable, because we know the mass scale for these guys. In order for them to be relevant for the electroweak phase transition, they really have to be around the electroweak scale of something like 250 GeV. So you do very naive estimate, the electric dipole moment you generate would be something like the electric charge because of coupling to photon, mass of the electron because you have to flip the polarity, is 2 root 16 pi squared downstairs. The mass scale is the electroweak scale, 1 over v squared, times the size of the CP asymmetry. If you put these things together, you would predict it's 10 to the minus 22 centimeter times the size of the CP violation. So even if you think that you can have 100% efficiency for creating a symmetry, so that size of CP violation itself may be 10 to the minus 3, you put 10 to the minus 3 here, that's 10 to the minus 25, which is 4 orders of magnitude bigger than the experimental limit. And of course, in explicit models, people do compute these things more carefully, and some people do claim that you can still evade the limit somehow, but you can see it's already very tight. You have to somehow avoid this 4 orders of magnitude problem so that you can live with this limit from the Acme collaboration on electric dipole moment. So this is really put in tight corner. So somehow the original idea of testable, viable theory of electroweak baryogenesis is more or less dashed. But we have to do something different then. And so here's my proposal. So we have the standard model with SU3, SU2 equals U1 with 3 generations. Let's say there's another standard model with this SU2, SU3, and SU1. Let's say only 1 generation for simplicity. I raise the scale just a little bit up. And on this side, you have 2 Higgs doublets so that you can have CP violation. And if the Higgs in that sector is light enough, you can have the first order phase transition, because it has nothing to do with the Higgs we discovered at the LHC. So suppose you do that. Then, at this first order phase transition, and some heavy fermions get bounced off from the bubble walls. And here I make a little exotic assumption that what's heavy in this sector is actually leptons. So basically, sort of taus play the role of top quark in this sector. And that generates the lepton asymmetry. And of course, B minus L is conserved, you generate the same amount of baryon and lepton asymmetries. But what's interesting about the leptons is that you can stick in, again, right-handed neutrino, which can connect two sectors, called the neutrino portal. Then, the lepton asymmetry you generated here just decays into the lepton asymmetry in the standard model. And assuming that happens above the electroweak temperature on our side, then whatever lepton asymmetry you generate gets converted to baryon asymmetry by spheron anyway. So this is the way you can generate asymmetries on both. And then on this dark side, I assume the quarks are actually light compared to the confinement scale of SU3. So at this stage, you converted part of the lepton asymmetry to the standard model, but this baryon asymmetry is still there. And as a result, when SU3 confines, you generate these baryons, which can no longer annihilate with antibaryons because asymmetry is already there. And if you have some protons around, to maintain charge neutrality, you also need to have pi minus around at the same time. Now, remember, there are no light leptons in this theory, so you can't compensate proton charge by a lepton. You have to compensate it by a hadron, and that's the only candidate is pi minus. And because everything is strongly coupled, any symmetric component, like P and remaining P bar, would quickly annihilate into pi naughts. And pi plus and pi minus annihilate into pi naught. And pi naught can decay into the standard model because there is additional photon in this sector, and that photon can mix into the standard model photon, which is what we call the kinetic mixing, and then all the entropy in the dark sector get dumped into the standard model at the end of the day, so there's no remnant except for this asymmetric component. So the way it works is that the first order phase transition in the dark sector first produces the same amount of baryon and leptons, but because of this right-hand neutrino connecting two sectors, this lepton asymmetry starts to decay partially into the standard model lepton asymmetry, and that in the end also induces the baryon asymmetry from the standard model spheron. And at the end of the day, these leptons are all massive, so they decay into the standard model, and so you have nothing left here. But you do have this asymmetric component of the baryon in the dark sector. That becomes a dark matter. So dark neutron, dark proton are the dark matter. And you also have finite baryon asymmetry in our sector as well. And everything is well defined. So in order to compute standard model baryon number out from the original asymmetry over here, you basically just need to look at the number of degrees of freedom in the system. And the only difference is whether these heavy leptons would decay into the standard model above or below the spheron temperature on the standard model side. So you get different coefficients here and there. And so that actually leads to a different estimates on the mass of the baryons in the dark sector. And this is an extra slide. I'm going to skip this. And this is a slide I meant to tell you that if you have this dark matter, which is multi-component, with having both proton and pi minus in it, in principle, they can scatter through the delta resonance in the galactic halo. And having a resonance scattering is a way of explaining what is called the core-cusp problem in small galaxies. But on the other hand, you don't want to have too large an interaction on the scale of the clusters of galaxies. It's controversial, so I don't insist on it. But nonetheless, this is an option you can have by using this kind of hadronic dark matter coming from this theory. And so that's the idea. And just a little bit of history here. So this idea that dark matter may be a asymmetric leftover in whatever new physics theory you're looking at. And the earliest paper I could find is the one from Lusinov, where he tried to use the technicolor theories of electrosymmetry breaking to generate the asymmetric dark matter. And I did some work on that too. But more recently, sort of modern incarnation has been really emphasized by Marcus in the audience here today. And so this became one of the popular ideas of dark matter now. And Catherine Zurek afterwards also worked with Jesse Shelton to combine this idea of doing electroweak baryogenesis type baryogenesis in the dark sector and get the asymmetric dark matter. So our proposal is along this line of thinking. But none of these models have been really UV complete and predictive, so we just make it completely well-defined. And once the model is well-defined, you can look into experimental signatures. So our light neutrino has small component of the heavy neutrino coming from this mixing between two sectors. And there are various experimental constraints. Charge current universality of the weak interaction tells you that this mixture squared has to be less than 10 to the minus 3. If you look at the flavor changing constraints, the constraints are actually stronger. It turns out that from Z decay, Z can decay into neutrino and a slight mixture of this heavy neutrino. And heavy neutrino then further decays into charged lepton and some visible final state. A Delphi experiment had looked into this. So typically, for most range of the masses, this mixing squared is less than -5. So it's a small mixing, which is not unnatural, which basically says that this new neutrino, like the neutrino, basically lives in the dark sector only with tiny coupling to the standard model. So then you can satisfy these limits. And this is a Delphi paper as a function of the mass of the right-handed neutrino here. And this is the limit on this epsilon squared in my notation, which is like 10 to the minus 4, 10 to the minus 5. But this is interesting because people now talk about new E plus E minus machine as a Higgs factory. And the LEP basically produces mega Z, about a few million Z's. And IOC can be retuned to be a giga Z machine, 1,000 times more. FCCEE is supposed to be tera Z, so a million times more. So you can push this limit further down quite a bit. So that's the opportunity for discoveries. In the same way, if the mixing angle is slightly larger, for example, in this heavy end of the mass spectrum, the standard model Higgs can also decay into our neutrino and this right-handed neutrino due to this small Eckart coupling. And that can give you the branching fraction of the order 10 to the minus 4. And that's something you can also probe by these future Higgs factories. So that's something you can look for. Also, this connection of letting pi not decay into the standard model required this kinetic mixing between the dark photon and our photon. And so that is really constrained by a plethora of experiments done on the laboratories and also constrained from supernova. Below this mixing, you don't actually let the dark photon decay sufficiently fast enough, so you don't want to be down here. So above this line, then you have these constraints already. And the amazing thing is that there are many, many experiments that are underway or going to be done, which can probe a lot of the part of this parameter space that's still left. And in particular, one thing I'm looking forward to is this Bell 2 experiment, which has started as a B factory experiment, an E plus E minus experiment in Japan. And they would attain something like 50 inverse Aldebaran, which is unthinkable integrated luminosity, and that will bring down this limit down to this level. So, all these experiments combined together will really close in on this parameter space, and so we might actually find this dark photon at some point. And these two plots are different because I make a different assumption whether dark neutron is lighter than dark proton, or dark proton is lighter than dark neutron. If dark proton is lighter, then dark proton is the major component of the dark matter today, and dark proton is charged, so couples to dark photon, and that mixes into a photon, which couples to ordinary nuclei. So that's an opportunity for direct detection experiment. It turns out, if you just do a simple naive analysis based on this Migdal effect in the direct detection experiment, Xeno 1 ton, you really exclude the parameter space down to here. Of course, you still have the parameter space left, but this is a significant constraint. Of course, we don't know if the electric charge in the dark sector is the same as our charge, maybe smaller, or maybe there's a mixture of both neutron and proton, so we don't quite know. But these are the two extreme limits, So you can probe this range of quantum space by direct detection experiments. And of course, as expected originally from the original idea of the electroweak baryogenesis, you do need first-order phase transition, which does lead to stochastic gravitational waves from the bubble coalescence. And for this range of the quantum space, again, various future missions are sensitive to the gravitational wave background from that. And one last curious thing I noticed just last Friday is that in principle, you can have dark neutron also decay into the standard model because the SU2 gauge group in the dark sector has an instanton that gives you this operator, and UDD is the dark neutron now mixing into dark neutrino, which then mixes into our neutrino and decay down to the standard model particles. It does require rather large gauge coupling constant because it's an exponential suppression. You need alpha weak in the dark sector to be bigger than 0.3 or so, but we have no idea how big the coupling should be in the dark sector, so it's certainly not excluded. Then you can have this decay of dark neutron happening today in the galactic halos, and the experimental limit is something like 10 to 25 seconds. So that's where this number came from, 0.3. And it was actually dreamed by Harold Tooth when he wrote this paper on instanton that he hoped to see proton decay using a instanton, which doesn't happen in the standard model simply because there are 3 generations. You have to change the baryon number by 3 units. But if the dark sector has only 1 generation, it could have happened over there. So that would be a kind of curious possibility. So summing up the second half of my talk, electroweak baryogenesis was touted to be a testable theory of baryogenesis, but it happened to be too testable and it's probably dead. So the idea here is to do it in the dark sector. So just simply copying the standard model with 1 generation, then you can have CP violation in the Higgs sector, you can have first order phase transition, and you can transfer the asymmetry to the standard model. And then you would predict that the dark neutron, if the dark proton is suppressed, of 1.33 GeV or 1.58 GeV, depending on the order of decay in spectral transition, would be the correct abundance for the dark matter. This is the first time I've written a paper where I had 3 significant digits in predicting the mass of the dark matter, so I was kind of happy about that. Or you could have this multi-component dark matter with proton and negative time. And even though these things are happening in the dark sector, there is an amazing array of potential experimental signatures. Dark photon is being searched for in a variety of experiments. There can be exotic Z decay, Higgs decay in future E plus E minus Higgs factories. And Bell 2 is already looking for dark photon. Even LHCb can look for the meson decay into dark photon. That covers part of the quantum space. Many ideas of being done experiments. And the first order phase transition is a requirement in this scenario and does lead to the gravitational wave signature. And this is just a potential possibility that instant-induced the dark neutron decay may be happening in halos today. And one of the motivations people had in talking about this kind of asymmetric dark matter is what Marcus emphasized. We have this coincidence that dark matter and baryon, which seem to have totally different origins, are the same within a factor of 6. In big scheme of things, factor of 6 seems like basically the same number. And so if you want to understand this on top of what I mentioned today, if you do have 3 generations instead of 1 generation, and if you have some kind of unification happening at high scale, that gauge coupling constants in 2 sectors are the same, then they run the same way with the same particle content all the way down to QCD scale. So you would predict indeed the mass of the dark baryon would be about GeV. So that may be the way we can also answer this question about this coincidence. So to finish up, so I started my talk emphasizing baryon asymmetry, but in the first half, that had a lot of connection with the neutrino mass and even with inflation. In the second case, had a lot of connection with dark matter. And so, so that's what I wanted to tell you today. And just in retrospect, when I got into grad school, that was a time when the string theory was in vogue, and so there was the sentiment that theorists are very confident, they know what they're doing. They have been complaining that experimentalists are having very hard time catching up. But it looks like these things have been totally turned around, and we're now being threatened by this amazing results coming from the experiments. So, in some sense, this is a healthy field. But what I try to emphasize today is that we are not dead. There are still many things we can look forward to. Thank you.
So if there are relic dark neutrons, they just pass through ordinary nuclear matter without...
Yeah, because they don't have strong interaction with us. So they have strong interaction of their own. We have strong interaction of our own. But it's not the same strong interaction because it's different SU3 gauge groups. So that's this structure. But the reason why this is interesting is that because they have strong interaction among themselves, that's the way you can get rid of the symmetric component, which is typically most difficult thing to do in this series of asymmetric dark matter. You just would like to keep the asymmetric component, and strong interaction does that for you automatically. And in addition, you can also have self-interaction, which may be also a good thing for the purpose of understanding the density profile of the dark matter in galactic field.
So why the dark sector should be similar to the standard model?
That's a good question. I wondered about that too. And I think the short answer is that SU3 equals SU2 equals U1 is a well thought out gauge group. If you want to write down a model, which has anomalies in it, because you need to generate asymmetry, but still totally anomaly-free for all the gauge transformations. Coming up with a gauge group with simple particle content is not trivial. You can do it, you can have other gauge groups and other particle contents, but what we got in the standard model is one of the simplest examples, which is totally consistent, free of gauge anomalies. So somehow, this structure is very good.
So I have a question for the dark sector simulation. How do you question that no matter what you put in dark sector, but still whether 1, 3 loop or 4 loop order, you may generate EDM.
Right.
So in your model, what's the EDM you're expecting?
Yeah, so this mixing I mentioned
Yeah.
from the left constraint is down at the level of epsilon squared less than 10 to minus 5. So in addition to simple estimates I have given, you have additional factor of 10 to minus 5 suppressing
right.
it. So if the experiments make additional, maybe order or 2 orders of magnitude improvement, it might be visible.
Okay.
But at least right now, it looks totally safe.
So I know it's not a central part of your talk, but you did mention one acronym, which was ILC. I'm wondering if you can give us any comments.
Right. So ILC has been discussed for a long time. My PhD thesis was about linear colliders. So it's been around for a long time. And so right now there have been serious discussions in Japan. What would happen in 2 days, 30th of January in Japanese time zone, is the announcement from the Japanese Science Council, which had been looking into this whole list of possible future major scientific projects, and they come up with a high priority list of that. And we already know that IOC will be on list of what they put forward, but there is a further selected list of selected projects which they consider to be higher priority, and whether IOC would make it into the list, we will know on the 30th. So that's one step people are watching for. At the same time, what I'm hearing from people like Jim Seacrest is that the U.S. State Department is now getting very serious about IOC. They would like to have a more collaboration on major technical infrastructure between Japan and the United States. And the U.S. has already started to play even a role of being broker to bring not only U.S. and Japan, but Europe together into this. The last meeting I was sort of in Washington, D.C., is that U.S. State Department called in science attaché from various embassies when Japanese delegate was visiting, and embassies are from Italy, Germany, France, UK, there was one more country I temporarily forgot. So the U.S. is now trying to play even more proactive role in bringing sort of coalition behind IOC together. So that sounds great. Of course, that doesn't guarantee anything yet, but at least that's probably something necessary.
So So any other question? If no question, let's thank Hitoshi.
Okay, thank you for the
By the way, after this talk, Hitoshi want to talk another topic about this why can this matter theory you don't have a Lorentz symmetry, the Boston theorem does not apply. If you want to hear, you can stay. But if you are
You're free to leave.
you're free, yeah, that's true.
Let's
You're free
take
to
a
leave.
few minute break.
Yeah,
anyway.
yeah.
Let's take a break a little bit.
Yeah.
Okay, thank you. Thank you.
Baryogenesis.
Yeah, yeah.
Oh, because how much people have given up.
Okay, given up. I wanted to talk to you about that. I don't think the people have given up on it. The thing is that, you know, I'm not an expert on
That's right. Equivalent means they say, all the ages are same. That's right. Thank you. Thank you.
You know, whenever you
Somebody somewhere will notice.
That's right. I just spoke.
Thank you. Sociologically, I don't think that people have.
So sociologically, my sociological piece of that is that
I wanted to reflect on
Okay, so we could,
I've not been following it.
trying to be present because I recall, you know, decades ago when this stuff was starting to happen, getting really weary of how people speculate about all these Feynman calculations that people were not doing, and it all seemed very, very dependent on just a lot of speculation. And the flavor I got from what he was saying is that there was enough leverage of enough important things, even with all these uncertainties about exactly
Yeah, I mean,
how
I
bubbles
think there are a lot of uncertainties. So I think that one source of uncertainty is
For your left
can
analysis,
you really just
let's
how
say
given a model
you need to get
how
a network
accurately
into
Can you get the answer? Yes.
say for the electroweak baryogenesis, we know this whatever baryon.
I did assume something. So I assumed that this neutrino sector has a Yukawa coupling, which is sort of similarly hierarchical for electron the Yukawa couplings. And I assume that global hierarchy is level something like a 1/10 each something. So it ends up being some high powers of that hierarchy. So in principle, you can get much bigger asymmetry if you like.
That's
you know, it definitely suggests that those signals should be there, right? And just like he was describing, it's somehow circumstantial, but you know, science doesn't always give you a big sign, you know, that points to one particular model. So, you know, so I think that the excitement is around it is that, you know, there are a number of different directions that you could probe.
And we might be led in that.
Suppose you found EDMs at the next level of experimental sensitivity. I actually wanted to ask you, and he kind of had the same question. You know, I haven't really been following electroweak baryogenesis. I mean, you presented a pretty, negative, view of what a sort of a conventional electroweak baryogenesis model would be. I mean, I didn't, I had the impression that there was more freedom in these EDMs and so on. Is it a question of model building, or do you think there's really a model-independent need for some unexplained cancellation? Could you just say a little more about
so the
that?
order of magnitude
Because you looked at
dimension
it,
is
yeah.
pretty model independent, because for anything that's happening at the electroweak scale, you can draw that kind of fluid diagram. So that
But
was.
if you have multiple, if you had multiple sources of CP violation.
So they can cancel against each other.
So, but you're not, you couldn't do something like, the CP violation you need for the baryon asymmetry involves the top core. This measurement involves the electron. So is there some,
But the diagram I drew is basically that electron, some gauge bosons, and something is running within a loop.
Yeah. So there's no flavor in particular.
No,
Right? That's
no.
So you're saying that if this new CP violation is flavor independent, then there's this.
Right.
Right. So no, I haven't really
Do you
studied
have
that.
like a favorite paper that sort of spells out what you had on the sort of